Hi guys, welcome to the channel. So far we have discussed about linear regression and simple linear regression. In this video we will go through a Pythonic implementation of simple linear regression from scratch. But before that, let me just walk you through some points as a revision that we have already discussed in the last 3 to 4 videos. Okay, so we have seen that the simple linear regression is mathematically given as y equal to beta naught plus beta 1x plus epsilon. Okay, we also went through some of the assumptions of linear regression, which are given as linearity of relationship. That means dependent variable and independent variable both are linearly related to each other, right? There should not be any multicollinearity. That means two or more independent variables should not be correlated with each other. The variance of error is always constant. Okay, this term is also known as homoscedasticity. Skedasticity. Okay, when the variance of error is constant, then it is said as the case of homoscedasticity. When there is violation of this error, for example, let's say the variance of error is not constant, it is varying, then that case is said to be as heteroscedasticity. Heteroscedasticity. These are the two new terms related to this particular assumption. The fourth assumptions we discussed about error term was errors are independent with each other. Two or more errors are not correlated with each other. They are not at any way related to each other. The fifth was errors are normally distributed. Okay, these were the assumptions that we discussed in the, I think, second video or so. Now after that we also went through the cost function of linear regression, which is given by y sum of squares of y actual minus y predicted values, which is nothing but y minus beta naught plus beta 1 x and whole square summed over from I equal to 1 to n. So this is your error term. This is your cost function given in linear regression, and this is your error term. Your error term is given as y actual minus y predicted. This is your error term, or you can also write it as y minus beta naught plus beta 1 x. This is your error term. These both are same. Okay, now this cost function is also known as residual sum of squares that we discussed in the last video. That is residual sum of squares. Okay, we also call it as ordinary least squares, if you remember from last video. In addition to that, related to cost function, we also discussed why we try to minimize the exact or some the absolute value of this error. Why we don't minimize the absolute value of this error and exact value of this error. Instead, we minimize the sum of squares of the error. Okay, after that, in the last video we also saw the derivation or estimation of parameters beta naught and beta 1. We derived this by minimizing the cost function. Okay, if you remember, we took the derivative of the cost function with respect to beta naught and beta 1, and then from the two equations that we got, we derived the value of beta naught and beta 1 in terms of x and y. Okay, cool. So now let's start with the Python code to implement a simple linear regression. Okay, we will implement it from scratch by calculating beta naught and beta 1. So simple linear regression, okay, implementing simple linear regression means simply, if you remember the equation y equal to beta naught plus beta 1 x. Okay, we are given x and we want to predict y. So in order to predict y given the value of x, what we need the value of beta naught and we need the value of beta 1. So if we have some sample data given to us, we can calculate the value of beta naught and beta 1, and if we know the value of beta naught and beta 1, we can simply predict the value of any x that was not present during training, or you can say during the calculation of beta naught and beta 1. If y is unknown, given the x, we can predict using if we have value of beta naught and beta 1. This is simply your building simple linear regression. In by building simple linear regression, we try to find the value of beta naught and beta 1. Yeah, that's it in simple linear regression. So I have already written the code in Python. So simply I will walk you through the notebook. Let me just open the notebook. Yeah, all right, guys. So this is the notebook where we have, I have already implemented the code, written the code. Simply, I will walk you through the notebook and explain what we are doing at each step. Okay, one by one. So be patient with me. This notebook will also be available in the video description. So you can always go through the notebook and play around it if you want. You can refer the notebook whenever you want. Okay, so let's start with the notebook. So in the very first, we have imported few library that is related to data manipulation, data import, data creation, or you can say anything related to data we want to do. We can use pandas library. Just a second. Yeah, this pandas library for related to data wrangling, we use pandas library. NumPy is again used related to numbering related thing. Okay, numbers calculations, and matplotlib is used for your plotting the graph. Okay, now coming to the second part of code. Here in this part of code, we have tried to generate some synthetic data by or on our own using Python code. So if you see here, we have taken some 40 quarters. Okay, starting 2020 0101, and periods will be, that is 40 quarters. Frequency is quarterly earnings. Okay, QE is quarterly. Now we have generated quarterly revenue. That will be, the revenue value will be in between 50 and 500, and we are generating total 40 quarterly revenue. We are generating it randomly using Python. Okay, then we have calculated using the stock price with some dummy formula. Let's say the base stock price is 10, and with respect to the variation in quarterly revenue, there is some relation with the stock price that is varying in this way. Okay, and we have also added some noise term in it. There can be some noise. Okay, so stock price varies with revenue with some noise. This we have calculated. So you can see the data points. Sorry. Yeah, so you can see the data points here over here. Okay, so sorry. Yeah, so yeah, so this is the quarter. Okay, you can see 2020. This is the quarter for March quarter, June quarter, September quarter, December quarter, and for every quarter we have got some revenue generated, and then that particular companies, what is the stock price when the quarterly revenue reported was this much, what was the relation or what was the variation in stock price. This we can see over here. Okay, so let's move to next cell. Yeah, just a second. So here in this cell, we have tried we have tried to calculate beta naught and beta 1. Okay, so let's see. So at the very beginning, first we have separated the dependent variable and independent variable. So first one is independent and second one is dependent variable, x and y, quarterly revenue and stock price. Then if you remember, what was the formula to calculate beta naught? It was y bar, that is mean of y, that is dependent variable, minus beta 1 and mean of independent variable. And for calculating beta 1, what we had, in order to calculate beta 1, we had sum of y minus y bar that is independent variable I equal to 1 to n minus mean of independent variable, and then we had x, that is independent variable, minus x bar, that is mean of independent variable, and whole divided by summation I equal to 1 to n. This was independent variable minus mean of independent variable and whole squared. If you remember the formula to calculate beta naught and beta 1. So here we have calculated the mean of x, that is independent variable, and mean of dependent variable. Now we have calculated beta 1. In order to calculate value for beta 1, we have simple formula. Numerator, we calculated numerator, that is xi, x minus x bar, into yi minus y mean, okay, and summed over it, if you see here. Then we calculated denominator in the similar way, and we have got the value of beta 1. So if you see the equation of linear regression, y equal to beta naught plus beta 1 x, so it will look similar to a straight line equation, y equal to c plus mx. Okay, so this beta 1 is nothing but your slope of the straight line. Okay, so we call it as slope, that is numerator by denominator, and then calculating the intercept, that is beta naught, is y mean, that is the mean of dependent variable minus beta 1, and mean of independent variable, we have calculated it here. Now since we have now the value of beta naught and beta 1, since now we have now with us the value of beta naught and beta 1, we can now calculate the value of value of dependent variable given any independent variable value. So we have calculated y pred as this beta 1 into x plus beta naught, okay, mx plus b. Now we have our predicted y value with us. Now we have our predicted value of y with us. Now we can check the the squared error. Mean squared error is nothing but a metric. It is a metric to check the performance of the model already built. It is a metric to check the performance of model built. Okay, so we have y pred and we have y actual given to us, so we can simply calculate mean squared error as y, the actual value of y minus the predicted value of y, squared over it, and take the mean of all the values. So simply this is calculated as mean squared error. Now we have drawn the data points, the actual observations x and y, and the predicted value y, and plotted the linear regression line that we got. We have got y equal to beta naught plus beta 1 x. We have beta naught and beta 1. So using the slope and intercept, we can draw the regression line. So this is the regression line. Okay, you can see over here. These are the actual points. The blue points are actual points, and this is your regression line. This is your regression line. Okay, this is your regression line, and here you can see we have slope, that is the value of beta 1 at 0.05059, and the value of beta naught, that is the intercept, is 9.69, and we have got mean squared error as 3.095. okay, so just note these three values. Okay, this we have calculated using the formula of beta naught and beta 1, that is implemented simple linear regression simply from scratch. Now in the next lecture we will build simple linear regression using libraries. First is your sorry guys, there was a glitch. Okay, so just remember these three values: slope 0.5059 and intercept 9.69. note this. So in the next lecture, when we build a simple linear regression model using library scikit-learn and stats model, okay, first we will build using scikit-learn, and second we will build using stats model. model. There we will see we will get the exact same value for beta 1 and beta naught, and exact same value for mean square error. We will be using the same data, and we will also see that we will be getting the same exact same regression line as we have got it here. Okay, so that's all for this video, guys. Let's meet with you in the next video. Till then, thank you, bye.